Okay, in this session, we're going to talk about the self-supervised learning for vision and language. I'm Licheng from Facebook and Yen-Chun and Linjie from Microsoft. We three together will cover the literature work as well as the future work for the self-supervised learning and vision language, which is a quite hot topic nowadays. So as we have learned in the previous talks, to address the vision and language, actually all kinds of machine learning applications, we need a machine learning. Nowadays, the machine learning is like a chair of three legs: data, algorithm, and the compute. They're equally important. Lack of any of the three will make the chair falling down to the ground. So especially we hope our data to be as big as possible, and our computing resource to be as strong as possible. And we, as research scientists, are proposing better algorithm to solve those AI problems. So let's first look at the data. When people are talking about data, it's actually not strictly the raw data. People like supervised learning, which means we need both the raw data as well as the labels. However, the labels are fairly expensive. Let's take MS COCO's image captioning as one example. We do a simple calculation here. In MS COCO, there are 120,000 images. And if we aim to collect 5 sentences per image, and we pay, let's say, 15 cents per sentence, plus the 20% AWS processing fee, that's going to account for $108,000. And this amount of money is nearly like taking another PhD student to join your lab. But right now, we can only collect a data set. So that's expensive. That makes a follow-up question. Are these labeled data really necessary? So we all know the labels are good, but actually the raw data themselves contain some intrinsic features to help them to do the supervision for training as well. That is self-supervised learning. Let's first look at the computer vision side. So in computer vision, we could train a convolutional neural net, the CN, to colorize a gray image and to recover it back to its original colorful RGB image in order to learn the representation of the CN. Those colorful images are actually everywhere. Basically, you could download the images for free from, let's say, Google image search. Then you convert it back to the gray image, and our goal is to recover it back to the RGB image. And similarly, we could do the jigsaw puzzles, image in painting, and relative location prediction to learn the representations. All those tasks are with free labels, as the images are everywhere. And actually, we've already seen some promising progress in the self-supervised learning stage using these 4 types of very basic operations. So the learned features from those tasks could be directly applied to downstream tasks, like image captioning directly. And besides those 4 basic operations, recently we've also seen a boosting trend on the contrastive learning in the self-supervised learning for vision. For example, the listed 4 approaches like the CPC, CMC, MoCo, and the simple CLR has boosted performance to an even higher stage, which is quite exciting. And on the other side, in the past year, we've also seen a breakthrough in the natural language processing. So perhaps the most representative 2 works are the BERT and the GPT. And here I listed GPT-2, but actually last month, I guess we also have seen the giant and the crazy model GPT-3. So let's consider all the GPT models as GPT family. So for the modeling side, the left-hand side, the BERT model, use the transformer as the encoder. The right-hand side, GPT family, is using the transformer as the decoder. But let's firstly ignore the tech details about the 2 networks. But one key to their success is the free and large-scale data. So we can see the BERT was pre-trained on large-scale Wikipedia, and the GPT-2 or GPT family was pre-trained on the crawled large-scale news articles. So once we have the data, how are we going to use them? The typical training pipeline is a two-stage training procedure. Firstly, we are given a large amount of noisy and cheap data. So we firstly pre-train our model on top of a series of pre-training tasks. Of course, we need to design those tasks very carefully in order to make sure our pre-training is stable and robust. Then we adapt model to the downstream task by fine-tuning. Note, the downstream tasks are the data for the downstream tasks are typically relatively smaller, but also cleaner. So hopefully the fine-tuning from the pre-trained model could bring us a lot of benefit in terms of the downstream task accuracy. And as a vision and language, our pre-training data are typically lots of image and text pairs. And our downstream task is some well-defined specific vision and language problem. For example, here, I show the VQA, which is the visual question answering. One big issue about the self-supervised learning in vision language is the generalization capability. Previously, what we observed in the pre-trained models is the pre-trained models can only serve 1 or 2 downstream tasks in the vision and language. But recently, some of the pre-trained models could already be adapted into like nearly 10 downstream tasks, showing very powerful generalization ability. So what are those models? Here, I listed all the recent vision and language pre-training and fine-tuning models, which all just happened in the past half a year. So you can see how crazy this field is growing. During this period, we've also observed a huge jump of the performance accuracy on the downstream vision plus language tasks, like visual question answering, visual common sense reasoning, LVR, referring expression, image to text retrieval, text to image retrieval, image captioning, and so on. And similarly, we've also seen some of the works on the video and the language pre-training, where my friend Linjie will introduce to you in a while. But in my time, let's focus on the image text pre-training. Before moving to the details of those work, let's first look at what kind of pre-training data are we using. So typically, the pre-training data for vision and language are the image and text pairs. But compared with vision or language only, there's one additional requirement, which is the pairwise relationship. So is such kind of data also easy to get? The answer is yes. So I still remember when I was working on the project with my friends, there's a national alpaca farm day. So I searched alpaca on Instagram. Here's what I got. So in order to protect the user's privacy, we intentionally put some of the yellow masks on top of the users so that we don't know who he or she is. Yeah. But let's just focus on the general image content of the picture and the associated caption on the right-hand side. So the right-hand side said, fun visit to the harbor farms to visit some alpaca friends. So although this sentence is not perfectly describing the content, but at least it's highly relevant to the image content. You would see, I would say this is a good pair. Now let's look at another example. The right-hand side caption said it's a kiss from alpaca. And you're going to see the interaction between the alpaca and the girl in the picture. Here's the third example. The caption said the alpaca was actually walking me, but I'm okay with that. So you can see, although those sentences are not exactly describing the image content, but at least they are very highly relevant to the photos those users uploaded. So if we're not talking about the legal issue, whether we could use the data, they are basically everywhere. As for the research community, people typically use 4 public data sets, which is the MS COCO, visual genome dense captions, conceptual captions, and SBO captions. And they're probably currently the largest public data sets, which is focused on the image captioning, could be used for our training. So among them, the conceptual captions convert the alt text description from HTML web page into image and text pairs, which is free. And similarly, the SPBO captions crawl the photos and their associated text from Flickr back to like around 10 years ago. But one thing to be noticed here is the preparation of those data sets is not trivial. Because when we do the downstream tasks, we need to make sure the validation set and testing set of the downstream tasks would never have seen before during the pre-training stage. So here, I also provide a GitHub link here to help you to do the preparation and cleaning if you're interested. Okay, now let's look at how we extract the visual the features to represent both modalities, image and text. Given the input pair of the raw image and the sentence, one typical way is we convert the image into dense regions, and we also convert the sentence into a series of tokens. Then we're going to have a sequence of region features and the sequence of the text embeddings. But one thing I want to mention here is the visual features. There could be several ways to convert the input image into a sequence. So before 2017, people were used to using the grid level feature. And until 2018, actually slightly before 2018, Peter Anderson told us the regional features could work much better than the grid level feature. And he demonstrated the performance in terms of the VQA Challenger winner and the image captioning state-of-art performance. But what's interesting here is in this year, a new CVPR from the UMass and Facebook told us that the grid level feature could work in par or even better than the regional features. And this grid level feature also helped them to be the winner of this year VQA challenge. So as of what option should we make for the visual representation, I think it's still in debate, but I'm looking forward to seeing who's going to be the winner in the following year. All right, we have talked about the pre-training data. Let's now discuss about the algorithm, which is the model and the pre-training tasks. We first look at the model architecture. Although there are quite a few works in the past half year, we could simply categorize them into two lines of works. One is single stream model, and the other is two-stream model. Specifically, the VI Albert and LexMert could be categorized into the two-stream model, while all the others fall into the category of single stream model. So if you compare both sides, the two model architectures, you could find the basic network unit is the transformer. So let's take the single stream model as one example so that you could easily infer the detailed model architecture in the two stream model by yourself later on. Here, I show the uniter, which is a single stream model. It's composed of an image embedder, a text embedder, and a transformer in the middle. Specifically, in our image embedder, we firstly use faster RCN to extract the visual features for each region. We also encode the location feature for each region via a 7-dimensional feature. The 7-dimensional feature typically consists of top left corner position, bottom right position, relative area, relative width, and relative height for each region. And both the visual and location feature will be jointly fed through a FC layer, followed by a layer normalization layer. And similarly, in the text embedding side, for each word, we sum up its word embedding and the position embedding, followed by another layer normalization. Then we get the text representation. Then we feed the region representation and the token representation into the transformer. The transformer could be 12 layers or 24 layers, depending on how large the model could be. And each modality will then be interacted with each other inside the transformer. And hopefully in the end, on the top of the transformer, we get the output, which is the joint representation of both modalities. And given this model, we could apply different pre-training tasks on top of the output from the transformer. Today, I'm going to mainly talk about 3 pre-training tasks, which has been widely used in, I would say, nearly almost all those works in the literature. The first one is the mask language modeling. So we randomly mask out some words and we try to recover the missing ones. And similarly, we could also randomly mask out the visual regions and let the model to recover the missing regions. That's our second pre-training task, which is the mask region modeling. And the third pre-training task is called image text matching. So during training, we sample a positive pair of image and text or a negative pair of image and text, and we let the model to predict whether they are paired or not. Now let's look at the detail of each pre-training tasks. The first one is the mask language modeling. So as I mentioned, given the image and the sentence, we first convert them into regions, a sequence of regions and a sequence of words. Then we randomly mask out some words. This is going to give us the mask indices. And our goal is to recover those words at those mask positions. So our loss here is the negative log likelihood of those masked words. And our second pre-training task is mask region modeling. Now, instead of masking the words, now we are masking out those visual regions. And we hope to recover those regions at those masks as well. There could be several ways to do so. One way is the feature regression. So our raw feature from those regions are actually from the fast RCN. So if we make our transformer to output some feature of the same dimension as the fast RCN output, then we hope the output could be as close as the ground truth one from the fast RCN. So we could apply the L2 loss here on top of the difference between the two features, enforcing the similarity between the transformer output and the faster RCN output. Or we could do the mask region classification. So this time we try to predict the probability of the object class from the transformer. So in this case, we're going to have a probability or the distribution of all the object classes from the transformer. And similarly, the faster RCN would also output some probability. And if we pick the peak one, which is the most confident category from the faster RCN, in this example, it told us it should be a dog. Then we hope, then we could apply the cross entropy to help our transformer output to learn the object class category from the faster RCN prediction. That's the mask region classification. Or we could do a soft version of the classification. So instead of using the final class label of the faster RCN, we could also utilize the distribution from the faster RCN as the label. So for example, here, the pink distribution is the output from the faster RCN. And we hope our predict distribution to be as close to be as the ground truth one. So we could apply the KL divergence here as the loss function. So to some extent, we're trying to distill the knowledge from the faster RCN to the transformer. And finally, our third pre-training task is the image text matching. So each time we sample a pair of image and text, the positive pair is just from one pair from our original dataset. And the negative pair could be constructed like this way. We randomly replace the image with some randomly sampled image from other pairs. That's going to be one negative pair. Or similarly, we could replace the sentence with some randomly sampled sentence from the other pairs. That's going to be another pair. So each time we could sample one positive pair and two kinds of negative pairs. And our model is responsible for predicting whether they are paired or not. That's image text matching. So besides the three popular pre-training tasks, there could be more interesting ones. For example, the United also proposed the word region alignment. The VLP proposed left to right language modeling so that we could also incorporate image captioning as one downstream task. And 12-in-1 and Lexbird said we could said we should do multitask learning, moving the downstream tasks back to the pre-training stage. And Oscar, the recent paper, Oscar said, okay, now those papers are using tokens and regions only. I'm going to also use the text, and I'm going to enforce the multi-view alignment into each two pairs from the three sets. So these are all some other pre-training tasks that you could see from the other papers. But one follow-up question is, how do we know which pre-training task is better? So we have to fine-tune the pre-training model into downstream tasks and use the downstream metrics to measure them during the evaluation. Then we can tell whether the pre-training task is working or not. This procedure, honestly, is painful because every time we have to wait for the results from all downstream tasks before telling whether the pre-training is working or not. But I think it's worthwhile as the self-supervised learning on vision language did provide us a lot of benefits in terms of the final accuracy. So now I'm going to hand it over to Yen-Chun, my friend. He's going to tell us how to apply the pre-training model to different downstream tasks, and as well as some future directions in this exciting area. Okay, Yen-Chun.
Hi everyone, this is Yen-Chun from Microsoft. So let's continue to the downstream tasks. We will first introduce a common downstream task in vision and language area, and then we introduce how to apply the pre-trained models for fine-tuning on each of them. So first, I believe everybody is very familiar with VQA now after attending this tutorial. So we will use Uniter to illustrate all downstream adaptation process since it's easier. And all the adaptation are common to any other VLP models you will see. Note that most VLP model takes very similar approaches. So recall that vision and language pre-trained models takes one image and one text as input. So for VQA, question is the input text, and then the model will just predict the probability over all possible answers from the embedding of CLS token. Next, visual entailment is the evolved from natural language inference task from the NLP community. NLI is popular benchmark for NLP, and 4 out of 10 tasks in Glue are NLI. Similar to NLI, VE tests the model's understanding of logical relationship between image and text. Vision and language pre-trained models can easily adapt to this as well. So we simply feed the image and statement into the model and formulate it as a 3-way classification problem for entail, neutral, and contradict. NLVR2 requires the model to determine true or false of a given natural language statement about pair of images. This task consists of 2 images and 1 text statement, but most existing vision and language pre-trained models are pre-trained on single image text pair. So how can we deal with this? The common practice is to duplicate the text statement and combine one with each image. So therefore we can concatenate the 2 COS outputs representations and predict true or false. Next, visual common sense reasoning, or VCR, tests AI's model's capability to reason about common sense in a multiple choice setting. So this model is also required to further provide the rationale of why the model choose that answer. For this type of multiple choice questions, image and questions are duplicated for every answer choice. All CLS outputs will be used to predict a confidence score of the answer. So task 5, referring expressions. Given an image and a sentence or phrase, we ask model which object is being described. For example, here, given woman washing dishes, our model is supposed to click onto this woman in the middle. And each region representation will be used to predict a confidence score, and then cross-entropy loss is applied for training. Lastly, image text retrieval. This might be the most practical real-life application of vision and language research. So for example, we can see applications such as a smart album or image search. Given a sentence, we ask the computer to find the most relevant image. Or reversely, we could also do text retrieval. Given an image, we search the most relevant sentences from the text database. Okay. This adaptation is very straightforward and very similar to the image text matching pre-training introduced earlier. So now we've talked about data and algorithm. Now let's talk about the third leg of the chair, which is also super important, compute. For such kind of pre-training and fine-tuning pipeline, we need huge amount of computing resource. And then, so how can we best utilize our computing resources? So for boosting the training speed, we apply 3 important tricks: dynamic batching, gradient accumulation, and mixed precision training. Each of them contributes to the overall throughput of pre-training. So dynamic batching, the transformer self-attention operation is quadratic to the input length. A common practice we see in open source implementation is padding to the same maximum length. To cover most of the pre-training data, the maximum length are often set too long. We apply the technique frequently used in NLP to sort inputs by length before batching. So left side shows conventional batching, and the right side shows dynamic batching, which you can see we save a lot of computation, hence increasing the overall throughput. And then next, the second technique we use is gradient accumulation. So for a large model trained on multiple GPUs, or even scaling across multiple nodes, The bottleneck would be the cross GPU or cross node communication. This figure shows conventional or reduced distribution. This figure shows conventional or reduced distributed training. The pink represents the actual computation of the model, and the yellow is communication of parameter gradients. We can reduce communication frequency, hence increase the overall training throughput. And finally, we often use mixed precision training for the from the popular NVIDIA implementation Apex. In practice, we observe 2 to 4 times speedups and a reduction in GPU RAM usage. This table summarizes the pros and cons of each precision, and then, if you go to this GitHub, it's a pretty easy plug and play for mixing them in PyTorch. Okay, now we have introduced self-supervised learning and how to utilize it as the 3 important legs for modern machine learning, especially for vision and language area. Let's see what we have achieved with this line of work. So until early this year, you can achieve state-of-the-art on almost all vision and language tasks with the techniques we introduced so far in the talk. With only one exception of GQA, a visual reasoning task. The state-of-the-art is neural state machine, which involves more complex reasoning and graph structure. So moving forward, we have seen 3 ongoing directions to extend vision and language pre-training: interpretability, better visual features, and adversarial training. Given this superior performance boost of pre-training, we start wondering, what actually did those V+L models learn? Our group therefore proposed value, vision, and language understanding evaluation to reveal the secret behind the scene. Our study covers model architecture choices, single stream versus 2-stream models. And then we use attention weight probing and embedding probing. These attention or embedding are extracted from a frozen pre-trained models. Usually we train simple linear classifier on the probing tasks to quantitatively evaluate what pre-trained models have learned. Value probes VLP models from 3 aspects. First, visual probing. We study visual relations predicted by attention weights. And the next, linguistic probing. Common linguistics tasks for probing BERT are tested on some VLP models. And then third, cross-modality probing. We study the visual coreference and multi-modal fusion degree and the modality importance of the VLP models LexMert and Uniter. So let's first discuss the visual probing part. So we propose to use visual relation detection. The task is to predict the existence or type of relationship between visual objects. For example, in this image, the guy wears the helmet. So we can, where is the relation? We use visual genome to construct this task using top 32 frequent relations. For linguistic probing, we follow standard practices on BERT with 3 types of tasks: surface tasks, syntactic tasks, and semantic tasks. We conduct 3 probing tasks to better understand their cross-modality behavior for VLP models. This study is unique for vision and language pre-training because vision-only or language-only models operates on single modality. So due to time limitation, we will not go into the details here, but list them here for completeness. To conclude, we list the final findings here. So first, cross-modal fusion. For a single stream model, deeper layers have more cross-model fusion, and the upset for two-stream model, we use uniter and Lexmert in the experiments. And then second, text modality is more important than image. Third, in single stream model, some heads only focus on cross-model interaction only. And then fourth, visual relations are learned in pre-training, although we do cross-modality pre-training. And then fifth, linguistic knowledge can be found, and it might actually be preserved from pre-trained BERT models since uniter and Lexmert uses BERT for initialization. Value is the very first step towards understanding of VLP models. An interesting next step would be, how to apply this model for compression. Another trend we see is to improve the visual feature being fed into the model. Most models we discuss here use a frozen CNN to extract region features. This might be undesirable because the pre-trained models could be limited by the quality of the chosen CNN. The first work trying to address this issue is VLBERT, which proposed end-to-end optimization for the faster RCNN feature extractor. The red part. And however, the detection of bounding box is non-differentiable in the pre-training stage, which could still limit the final overall performance. Therefore, recently we see PixelBERT. They propose to solve the issue altogether by applying transformer models directly on grid outputs of CNN and optimizing end-to-end. The key technique to make this work is the pixel dropout, which acts as a regularization term and saves computation. Another recent work, Oscar, used the object tags circled in red from the visual detector as the input. Since the tags are obtained from the image, it can be viewed as enhanced image feature. Oscar significantly boosts the performance of image text retrieval on COCO and image captioning. Okay, finally, we introduced the latest advance in vision language pre-training, VILA, Vision and Language Large-Scale Adversarial Training. Adversarial perturbation is applied to the inputs at training and results in better final accuracy. We briefly introduce VILA here. VILA has two stages, task-agnostic adversarial pre-training and task-specific adversarial pre-training. For the adversarial training stage, we utilize FreeLB, a PGD-based adversarial training method that previously achieved state-of-the-art on NLP and apply additional KO divergence constraints to further improve the performance. So both adversarial pre-training and adversarial fine-tuning are shown effective individually. And by combining them, VILA achieves the new state-of-the-art. It is worth noting that VILA improves generalization. We do not observe trade-offs between accuracy and robustness as found in adversarial training for image. After these follow-up works, the state-of-the-arts are pushed further. Pre-training methods such as VILA and Oscar still dominates all the vision and language benchmarks. Note that the top one in VQA challenge this year, Grid Feature plus Movie, while not using pre-training, is somewhat related to better visual feature. And the state-of-the-art GQA model is still without vision language pre-training. Okay, so far, we have introduced the basic how-tos to achieve SOTA for vision and language tasks. We covered the public available datasets that can be used for pre-training. We discussed model architectures. Single stream transformer is a good default. We went through the basic pre-training objectives. Hopefully, our engineering tricks will help you speed up your deep learning workloads in the future sometime. From now on, everybody attending this talk can confidently say that they understand how supervised learning can be used for the data, algorithm, compute supporting legs of modern AI, especially in the vision and language area. We have also pointed out some ongoing research and possible future directions. We see study on the learned representation, which shed light on possible pruning compression for VLP. We see trends on improving visual features and maybe towards end-to-end training of the convolutional nets. However, visual reasoning tasks seems a little bit tricky to take advantage of self-supervised learning. This could be an interesting direction to work on. There are some other areas under vision and language beyond image and text. For example, vision and language navigation and video plus language pre-training. We are seeing self-supervised learning techniques applied to vision and language navigation. However, this field is beyond the scope of this tutorial, so we will not cover those papers. We will instead focus on video and language pre-training in the rest of the talk. My colleague Linjie will take over from here.
Thanks, Yen-Chun. So I'm Linjie from Microsoft, and for the last section of our talk, we will talk about self-supervised learning for video and language. So back to this timeline we have shown in the first section of our talk, we have just covered image plus text pre-training and some of its extensions. So in the last section of our talk, we will cover most of the existing video plus language works, such as How200M, VideoBERT, CBT, and etc. I will give a brief overview of them one by one. For video plus language pre-training, the input is usually a narrated video. The common practice to represent a video is to pre-process it into a sequence of image frames. If subtitles are not available, the narration audio can be transcribed by ASR to obtain the language input. There are two large datasets that provide both videos and their accompanying narrations or subtitles. One is TV dataset with 22,000 video clips from 6 TV shows. Each video clip is 60 to 90 seconds long with subtitles. The other is How200M dataset with more than 1 million instructional videos from YouTube. Each video is 6 minutes long on average with narrations in different languages. And most of existing pre-training works use How200M as their pre-training data. So next, I will introduce more details about How200M. In their paper, they not only presented a large-scale pre-training dataset, but also proposed a simple framework to learn joint video text embeddings. First, their large-scale pre-training dataset, as known as How200M, is cut into more than 100 million video clips spanning 23,000 activities across domains such as cooking, gardening, and fitness, and so on. They extracted 2 types of video features and concatenated them as video representations. One is 2D features from ImageNet pre-trained ResNet 152 model. The other is 3D features from Kinetics pre-trained ResNext 101 model. For text input, they use Google News pre-trained word-to-vec embeddings as their text representations. To learn the joint video text embeddings, 2 nonlinear functions are applied to the 2 features, video feature and text feature to embed them into a common embedding space. The pre-training is supervised by max margin ranking loss that encourages alignment between video clips and narrations. Here, alignment means whether a video clip and a narration is a match or not. Although the model architecture and the training framework proposed in this paper are very straightforward, they show promising results on two downstream tasks: weakly supervised step localization and clip retrieval. In weakly supervised step localization, the goal is to segment the input video clip into steps for instructional videos. In clip retrieval, given a natural language query, the goal is to match it to the most relevant video clip from the corpus. So in their paper, they show results first on step localization under weakly supervised setting. They show that how to 100M pre-trained model is better than training a fully supervised model on a small training set. On clip retrieval tasks, across different domains, for example, instructional videos and movies, how to 100M pre-training largely boosts model performance despite the domain differences. Lastly, they show that using more data for pre-training gives better results across all tasks. A concurrent work to how to 100M is VideoBERT, which is the first work to use transformer-based architecture on video plus language pre-training. Unlike how to 100M, VideoBERT encourages interactions between video frames and subtitles at an earlier stage. They collected more than 300,000 cooking videos from YouTube as their pre-training data. Text inputs are tokenized into word pieces following BERT. Video features are extracted from Kinetics pre-trained S3D model. And the main difference is that continuous high-dimensional video features are tokenized into 21,000 clusters using hierarchical k-means. Two pre-training tasks are applied to VideoBERT: masked language modeling, MLM, and masked frame modeling, MFM. Both are supervised with cross-entropy loss. So the pre-trained VideoBERT is applied to captioning and zero-shot action classification to demonstrate its power. For both tasks, text templates with mask tokens are constructed as text input. In this way, the two tasks are transformed into predicting the masked words in the text templates. Similar conclusions are observed for VideoBERT. On action classification under zero-shot setting, VideoBERT performs competitively to supervised method. On captioning, VideoBERT with fine-tuning outperforms state-of-the-art, and is further improved when adding S3D features to video tokens. They also show that using more pre-training data generally gives better results. Extending from VideoBERT, CBT is introduced by the same research group from Google. CBT is short for contrastive bidirectional transformer. This paper proposed video-only pre-training along with video plus language pre-training to learn better video representations. They presented a new model architecture with 3 transformers: BERT, CBT, cross-model transformer. The pre-training is supervised by 2 pre-training tasks, both with a noise contrastive estimation loss or NCE loss. NCE loss encourages the model to learn to identify the correct instance given the context compared to a set of negative distractors. The two pre-training tasks are end-to-end video-only pre-training for S3D and CBT, video text alignment pre-training for cross-model transformer and then CBT. It is applied to a variety of downstream tasks focusing on video-only inputs without subtitles or narrations. As we focus on video plus language tasks, we will only discuss their captioning results. On UCOOC2 captioning, they show that CBT achieves the new state-of-the-art, surpassing previous video BERT plus S3D results. As they claim, contrastive learning encourages better video representations. A similar work to CBT is later introduced by the How to 100M research team. It's called MIL-NCE. Note that they all also focus on learning better visual representations end-to-end. So the I3D, S3D, or F3D in their model is not pre-trained on kinetics. They proposed MIL-NCE pre-training. MIL stands for multiple instance learning, and NCE is short for noise contrastive estimation. It is similar to video text alignment pre-training task in CBT. However, given a clip, multiple narrations that happen close in time within the same video are considered as positive candidate. Therefore, the multiple instance learning as multiple positive candidates are considered. It is also applied to different downstream tasks, mostly focusing on video-only inputs. And we will only discuss their clip retrieval results. On zero-shot clip retrieval, they show results on two datasets, UCOOC2 and MSR-VTT. On both datasets, their method improves over How to 100M without using any labeled data. As I mentioned before, that their I3D or S3D model is not pre-trained on kinetics. On UCOOC2, their method even surpasses supervised How to 100M model. So the last work we will discuss is Uni-VILM. Uni-VILM presents similar model architecture to CBT, which also adopt three transformers, one for encoding text inputs, one for encoding video inputs, and the last one for modeling cross-model interactions. The key difference between Uni-VILM and the previous work is that Uni-VILM is applied to both video text generation task and video text understanding task. Firstly, Uni-VILM is pre-trained on all food domain related videos from YouTube. Secondly, Uni-VILM adopts a different pre-training paradigm with three pre-training tasks: MLM, MFM, and video text alignment. There are two downstream tasks considered during evaluation: captioning for video text generation and retrieval for video text understanding. Note that, different from previous works, Uni-VILM utilizes transcripts as additional input to the model for captioning. For retrieval, a query and a video clip are fed into the model to produce a score. So table on the top left shows clip retrieval results on UCOOC2 and MSR-VTT. We consider UCOOC2 as in domain while MSR-VTT as out of domain because Uni-VLM is pre-trained on cooking videos. On uCook2, Uni-VLM improves over How-to-100M with less pre-training data. On MSRVTT, their method surpasses How-to-100M with the same amount of pre-training data. However, considering that Uni-VLM adopts a more complex model architecture, the margin of performance improvement is not very surprising. Table on the bottom right shows captioning results. Although pre-training lifts the performance for Uni-VLM, the improvement is marginal compared to the state-of-the-art model, which did not utilize any additional data. So I have just given a high-level introduction to several existing video plus language pre-training works. You can read their paper for more details. To conclude, video plus language pre-training is still at its early stage. There are several limitations in current works. First, most works fuse video and language at a later stage. If early fused, video and language inputs are directly concatenated. Among all these methods, temporal alignment between videos and text are not explicitly exploited. Second, pre-training tasks are directly borrowed from image-text pre-training. For example, MLM is similar, MFM is similar to mask region modeling, and then image-text matching is similar to video-text alignment. There's no specific design proposed for video plus text pre-training. Third, pre-training datasets are limited to narrated instructional videos from YouTube. Also, video plus language downstream tasks considered in these works are relatively simple, as they mostly focus on visual clues only. Subtitle or narrations contain a lot of information, but usually discarded. We hope to see future works that could remedy these limitations and further push the model performance on video plus language tasks. And lastly, thank you for joining our talk. This will be our Q&A session for self-supervised learning.